Well, good afternoon, ladies and gentlemen. We're going to continue on with entropy and look at a particular kind of process that will crop up over and over and over again now that we have a little bit further grasp on entropy over the last several days. We're going to look at what's called isentropic processes. Isentropic processes refer to constant entropy properties, or of course, no change in entropy over the process. So remember, we had isobaric, isothermal, isochoric, adiabatic, isentropic, so constant entropy or no change in entropy process. Delta S is equal to 0 or constant over the process. So we're going to focus on isentropic processes involving ideal gases. That's mainly the application you're going to see this sort of thing this semester. So we're going to look at we're going to look at property relationships and how they reduce in the case of isentropic processes. We're going to look at the property relationship, see how they reduce for isentropic processes for constant specific heat and variable specific heat. And then we'll do an example today, okay? So we're going to derive some isentropic property relationships, how temperature, pressure, specific volume, how they're all related when the process is isentropic, entropy doesn't change or is constant, okay? So let's get started here. So isentropic processes. Isentropic processes. So on a TS diagram, so here's temperature, maybe there's some isobars in here. So here's pressure. So isentropic processes refer to a movement up or down vertically along a line of constant entropy. So an example would be some sort of heating, some sort of compression process going from some pressure to another pressure, or raising the temperature of some sort of a gas or something by compressing it and increasing the pressure going from state 1 to state 2. So this would be a piston cylinder device containing some kind of a gas, state 1, and a temperature T1 and P1. And then let's say it's adiabatic process here. We wrap some insulation around it. And let's compress the piston down, raising the pressure, raising the temperature. So the piston goes downwards. So we have some sort of an isentropic compression to a temperature T2 and P2. All right, so that might be what's going on in this TS diagram here. Some sort of an isentropic compression process of a gas. Pressure goes up. So here's P1 and here's P2, okay? So that's an example. Now, where do isentropic processes tend to crop up? Well, let's write the entropy balance for a closed system. So here we have a closed system here, going from state 1 to state 2. Okay, so we have S1 and S2. So if we write the entropy balance on our system, it's a closed system. We can see that here. We see delta S from 1 to 2 is equal to the sum of the integral of del Q over the interaction temperature plus entropy generated due to irreversibility over the process, okay? Now, if this particular process involves no heat transfer, so let's say adiabatic, it's adiabatic, so that means the heat transfer term goes to 0. And if it is reversible, If it's reversible, then S gen is equal to 0. 0 reversible, 0 adiabatic. Okay. Then, of course, we have delta S equaling 0, or a isentropic process. Delta S 1 to 2 equals 0. Isentropic. So if we have reversible adiabatic processes going on for a closed system, that usually implies that it is a isentropic process. But of course, you need to write the entropy balance and see whether it is an isentropic process. Want to write that out for yourself to justify, okay? So when we have reversible adiabatic processes for a closed system, usually that implies an isentropic process, or delta S is equal to 0. Let's develop some relationships between pressure, temperature, or volume, or specific volume for, let's say, an ideal gas under the constraint of an isentropic process. So let's get an equation that relates, let's say, temperature and pressure, or temperature and volume, or specific volume, as for an isentropic process. So the isentropic property relationships, ideal gas, so IGB, ideal gas behavior, isentropic prop relationships. And we're going to look at constant specific heats first. Constant CP and CV, constant specific heats. Okay, so we previously had two equations that were valid for an overall process, ideal gas behavior, constant specific heats. As you recall, we had two equations. We had delta S, or the change in specific entropy from state 1 to state 2, equal, and I had two expressions. I had CP ln T2 over T1 plus R ln P2 over P1. Okay, that was one expression. We developed this a lecture or two ago. I think it was 2 lectures ago. And then we had, so this was based on enthalpy. That's why it's got a CP in there. And then we had CV ln T2 over T1 minus R ln V2 over V1. This can be specific volume or volume, doesn't matter. The masses cancel out in the fraction, okay? So if delta S is equal to 0, so this guy is equal to 0 for an isentropic process, then that implies, so let's look at the first equation here. That implies CP ln T2 over T1 equals minus R ln P2 over P1. Okay? Now I'm going to divide both sides of the equation by the specific heat, CP. So I get ln T2 over T1 equals R over CP ln P2 over P1, okay? Now CP, well, tell you what, R, for an ideal gas, what's the relationship between specific heats and the gas constant R? So recall, for IGB, CP minus CV is equal to R. Or if you like, Cp is equal to Cv plus R. We had that relation, we had that result several weeks ago, okay? Long time ago, long time ago. So I'm going to make a substitution for R here. So we get Cp minus Cv over Cp. That's what that ratio is, R over Cp. And then that gives me 1 minus Cv over Cp. 1 minus Cp over Cv. Now, Cp over Cv, I only mentioned this one time. There's a quantity K. K is referred to as the ratio Cp over Cv. We talked about this a while back, but let me remind you, we have a symbol, a quantity that gives you the ratio of specific heats. Let me show you here. Let's go to the ideal gas tables, and I'll remind you where K is shown. So here we have specific heats. All right, table B10, ideal gas specific heats for various gases. Temperature, Cp, Cv, the ratio. Here's K. K for various gases as a function of temperature. Why? Because Cp and Cv vary with temperature. So K, which is the ratio of Cp over Cv, varies with temperature. I should have one for air. Here's air. Oops. I guess air is up here. Yeah, so here's air. So if you need specific, if you need the ratio of Cp over Cv to do a calculation, then you can look it up in table B10. So K is a function of temperature, just like Cp and Cv are functions of temperature. After all, K is the ratio of Cp over Cv. So this quantity here, Cv over Cp, is 1 over K. So this whole thing is 1 minus 1 over K. All right? Okay, so let me write the last. So we got 1 minus 1 over K, natural log P2 over P1. Okay? Now I'm going to take this quantity in parentheses here and stick it inside the natural log, so multiplication becomes exponentiation. So this implies ln T2 over T1 equals ln P2 over P1, and then I've got in the exponent 1 minus 1 over K. Okay, so that's inside the natural log. Let's raise everything to the nth power and get rid of the natural log. And I get T2 over T1 is equal to P2 over P1, 1 minus 1 over K. All right? So this is our first isentropic property relationship. It relates pressure and temperature at some initial and final state for an isentropic process. So let me get rid of this here, and I'm going to write right next to this equation. This implies T2 over T1 equals P2 over P1, 1 minus 1 over K, okay? You can do the same thing with the second equation involving pressure, involving specific volume. So you can go through the same derivation and you get a similar equation. I don't have them memorized. I always have to look them up. Let's see, we get the ratio of temperatures, T2 over T1 is equal to the ratio of the final to the initial specific volume. And then in the exponent, we have, let's see here, 1 minus k, 1 minus k, 1 minus k, all right? By the way, this first equation right here, sometimes the exponent is written a little bit differently. You can get everything with the same common denominator. I could multiply the 1 by k over k. So then that means the second and the first term are same denominator. And so I'll have a k minus 1 over k. You can write it like that as well. It's the same quantity, okay? So sometimes this is written as k minus 1 over k, all right? In fact, I think I have that in the notes. It's the same thing, all right? It's the same thing. Okay, so we have two isentropic property relationships relating temperature, pressure, and volume for a constant entropy process. So let me rewrite these here. T2 over T1 is equal to P2 over P1, 1 minus 1 over K, and that's the first one. And then I have T2 over T1 is equal to specific volume at state 2 over specific volume at state 1 minus K. So these are the isentropic property relationships valid for IGB, constant specific heats, and constant entropy. So IGB, constant CP, CV, and therefore K. K is the ratio of specific heats. Usually in these problems, you're told to evaluate K at some temperature. Just like in past problems, you were told to evaluate specific heat at some temperature, okay? So IGB, constant specific heat, delta S from 1 to 2 is 0. In other words, isentropic process. So there's your isentropic property. Oh, sorry about that. Let's just go over this again. So a little bit of algebra. On the first property relationship, delta S is equal to 0. And we arrive at T2 over T1 is equal to P2 over P1, 1 minus K over 1 minus 1 over K. Luckily, I think you can see a small version of the screen while I'm working. Sorry about that. And then we did the same thing with the second equation on a property relationship. And we had T2 over T1, V2 over V1 to the 1 minus K power, okay? So these are both valid for constant specific heat, delta S equals 0, isentropic process, IGB, okay? Now what's another way to relate properties, pressures, volumes for an isentropic processes? How do we do that? Well, how do we do that for variable specific heat? So how about variable specific heat? What are the relationships between temperature, pressure, and volume for a constant entropy or no change in entropy process if we have variable specific heats? So isentropic process, variable, isentropic property relationships. For variable specific heat. And again, this is for ideal gas behavior. So make sure IGB, ideal gas behavior, okay? Well, let's take a step back here And recall, we had an equation giving delta S for variable specific heats involving those S naught quantities. Remember, it was S naught evaluated at T2 minus S naught evaluated at T1. And then I had a plus R ln P2 over P1. Okay? So if it's isentropic, delta S is equal to 0. All right? So isentropic, so delta S is equal to 0. So in theory, if you have, let's say, an initial temperature, and you have the two pressures, the initial and the final pressure, you can look S naught at T1 up in a table. You can calculate this quantity, and therefore you could calculate S naught at T2. And then you could back out the temperature using a IGB table to get T2. So you could use this equation. You could use this equation with the left-hand side. So I could do the following. I could say S naught T2 is equal to S naught T1. And then I have minus R ln P2 over P1. I could do that. Okay? I could do that. And I could, if I knew T1, I could get S naught at T1. And I know the pressures, so I can calculate this term. So I can get S naught at T2. Okay, I could do this. I could do this. All right? Now, there's an easier way to do this, a much easier way. And it utilizes reduced pressure. Remember reduced pressure? We were talking about the ideal gas law about a month ago. We introduced reduced pressures and reduced volumes and reduced temperatures. Well, there's a quick and easy way that these properties, pressures and temperatures, can be related for an isentropic process using reduced pressure. So you could do this. This is okay. I'll put a question mark here. Not very easy to do. It's laborious. We're going to do something else instead. We're going to say, for isentropic process, the reduced pressure PR2 over PR1 is equal to P2 over P1. Okay, where these reduced pressures, these are not the same reduced pressures, they're not numerically the same reduced pressures that we are used to with ideal gases, where we divide pressure by the critical temperature pressure. It's not the same thing. It's a rescaled pressure. So these reduced pressures here, these are available in tables. Tables, IGB tables, and they're a function of temperature. Function of temperature. So for example, so let's see how this would work. How would we use this expression? Let's say you are given let's say you're given that it's an isentropic process. You're given T1, you're given P1, and you're given P2. And you want to find temperature T2. That's what you want to find. Well, how would this work? So, procedure. You would first look up reduced pressure PR evaluated at temperature T1 from an IGB table. Let me show you here what this might look like. So here we have IGB tables for air, HU S naught, function of temperature, reduced pressure, PR, as a function of temperature. So if you have T1, you would find PR1 by finding the temperature and then going over horizontally to get PR. Maybe you have to interpolate, who knows? Who knows? Maybe you have to interpolate, who knows? So look up PR evaluated at T1. Then you would calculate PR2 is equal to, I would use this equation, PR1 times the pressure ratio, P2 over P1. I've got the reduced pressure temperature T1. I have the pressures to get the pressure ratio. Therefore, I have PR2. Look up temperature evaluated at P, so T2, to get T2, find the final temperature, which is equal to the temperature evaluated at PR2. And you would look this up from a table. So once you have PR2, you would go to your table. So let's say you knew what PR2 was at state 2. You would find it and then go over and get the final temperature at state 2. So this procedure allows you to calculate temperature changes as a function of pressure using reduced pressures, and this incorporates variable specific heat. By the way, there's another way to do this. Let's say you were comparing, let's say you had temperatures and volumes instead of temperatures and pressures. You can relate, you can relate volumes to reduced volumes, which are a function of temperature. So also V reduced 2 over V reduced 1 is equal to V2 over V1, where these are reduced volumes, actually they're specific volume, and they're from tables. Okay, you could do the same procedure here if you had the volume ratio, you had an initial temperature, and instead you would be looking up reduced volumes instead of reduced pressures. Okay, so let's stop here for, maybe before we do, I want to point out, this is getting to be a lot of equations. And as I mentioned last time, I provided a nice table for you to kind of condense all this stuff you have to remember. Let's find it again. Let's see here. It's in tables, chapter 6. I think it's table 6.2. Here we go, right before open system entropy balance, which we're going to go to next time. Page 124 in the notes. You'll see it right here on the bottom. I have isentropic processes overall. So here we have equations for variable specific heat, constant specific heat property relationships. And so here's this PR and VR equations here, okay? PR and VR equations. So it just reminds you, condense what we've done today. And remember, these are the property relationships for entropy, differential overall, per unit mass, et cetera, et cetera. These are all provided for constant and variable specific heat, IGB, et cetera, in table 6.2. So this is I hope, a fairly helpful table that would condense a lot of the information. There's a lot of information here, so I think you need this table. We're going to get on and just do an example here in a moment. Okay, let's do an example here involving compression of air in a piston cylinder device. So we have an insulated piston cylinder device containing air. Starting off at state 1, the pressure and temperature at state 1 are 290 degrees Kelvin and 100 kPa. And then we do boundary work. We do boundary work on, or some kind of work, presumably boundary work, and compress the air, raising the pressure, raising the temperature. Okay? Final pressure, P2 is 800 kPa. Now, what do we want to find? We want to find the minimum specific work, lowercase w, W per unit mass, the minimum work required to compress the air from 100 to 800 kPa, adiabatically. Okay? No heat transfer, insulated. So what's the minimum work required to compress the air, to raise it up to a pressure of 800 kPa? All right? Okay, so let's get started here. Let's get started. Analysis. So minimum work. When you hear terms like maximum efficiency, max CLP, the maximum efficiency of something means that, or maximum COP, maximum coefficient of performance. When you hear that you want to minimize the work, which is similar to maximizing the coefficient of performance, irreversible process should pop into your mind. Reversible processes are the most efficient processes. They produce the most work for a work-producing device. They consume the least work for a work-consuming device. So if we want a minimum work, so min work, immediately to me that implies reversible process. So this compression process we have needs to be reversible. Of course, what that really means is no entropy is generated during the process. Okay? So let's write the entropy balance for our air. So our control volume here, let the system be the air. Okay. So here's our system, it's the air. So let's write the entropy balance for the air. Let's see if this gets us anywhere. So delta S, and I'm going to do this in lowercase. I'm going to do everything, well, I guess I'll do it in uppercase. Yeah, I'll do entropy, not specific entropy. So S balance, delta S from 1 to 2 is equal to the integral, the sum of the integrals of the heat transfer over the interaction temperature over the process plus S gen over the process. Now the piston cylinder device is insulated, so we're going to assume an adiabatic process, 0. Adiabatic. I'll write that in the assumptions in just a moment. And minimum work implies reversible process, so Sgen is 0. Reversible. So what this implies is delta S from 1 to 2 is 0, which also implies the change in specific entropy from state 1 to state 2 is 0. This is a isentropic process. Isentropic process. Reversible, adiabatic, therefore isentropic. Let me write this up in the assumptions. Assumptions. Isentropic, reversible, or if you like, isentropic. I'm sorry, reversible, let's just leave reversible, and then adiabatic. reversible, adiabatic. Okay. Now let's also apply the energy balance. Let's apply the energy balance to our air. Because we're interested in a work, a minimum work. Well, Q minus W is equal to delta E, which is equal to delta U. Why is it equal to delta U? Because I'm going to neglect changes in kinetic potential energy. No heat transfers, so that's 0. And so I get the work, and I'm going to write it, well, I get the work is equal to delta U, or if you like, the specific work from 1 to 2 is equal to the change in specific internal energy from 1 to 2, okay? So the expression, so let me write right over here, isentropic process. And W from 1 to 2, in other words, our minimum work, because it's an isentropic reversible adiabatic process, is going to be equal to delta U from 1 to 2. Okay, so let's just leave this equation here. So I need to find the change in internal energy from state 1 to state 2. Or if you like, U evaluated at temperature T2 minus U evaluated at temperature T1. Okay, so that's basically what we need to find. We need to find internal energies at state 1 and state 2, or we need to find delta U from state 1 to state 2. Now, let's look a little bit more carefully at the problem statement here. I want you to find the minimum work, and we're going to do it in one of two ways. We're going to assume constant specific heat to find the minimum work, and we are going to then, after that, assume variable specific heat to find the minimum work. Of course, the true value is variable specific heat, where the constant specific heat value gives us an approximation. For the minimum work. Okay. Now, note, I do provide K, which is CP over CV, 1.4, and I provide a CV value for you to evaluate the specific heat, 0.73. Okay. So you're actually given specific heat at constant volume, and you're given a K to use for the constant specific heat calculation. So let's do part A. So W1 to 2, by the way, I got rid of the negative sign here. What I mean by, I guess I'll put the negative sign there. I guess I want to be a little careful there. So, okay, so let's calculate using constant specific heats the minimum work. So A, constant CP, CV. So the minimum work is W1 to 2. W1 to 2 is equal to delta U, which is equal to CV delta T. Or if you like, CV T2 minus T1. Now remember, the process here is an isentropic one. So if I have a TS diagram, temperature, specific entropy, and here are my isobars. So here's P1, here's P2. We start off at a temperature T1. And we have, of course, a certain S. And the idea is we're going to go vertically up from state 1 to state 2. Okay, that's what the process is. We're going to end up at a temperature T2, of course. Isentropic process from temperature T1 to T2. Okay, that's what the process looks like on the TS diagram. So we know CV. I know T1. What is it? 290 degrees, something like that. Yeah. I need to know T2. Let's find T2. Let's see here for an isentropic process. 1 to 2 is isentropic. That means I can use an isentropic property relationship. T2 over T1 is equal to P2 over P1, 1 minus 1 over K. So there's our isentropic property relationship. Note, I know T1, I know the pressures, initial and final, and I'm given K. I have everything in this equation. I can immediately solve for T2. Let's see here. T2 is equal to T1, P1 over P2, 1 minus 1 over K. Let's see here. T1 is 290 degrees Kelvin. I'm sorry. P2 over P1, not P1 over P2. P1 and P2 are 100 and 800 kPa. 800 and 100 kPa, so we're pressurizing it. Eight hundred, 100. And we're taking that to the 1 minus 1 over, what's our K value? 1.4. 1.4. And let's find T2 here. So what's T2? T2 is equal to 525 degrees Kelvin. 525 degrees Kelvin. 525.0 degrees Kelvin. 525 degrees Kelvin. Great, so I know temperature T2 now for this isentropic process. Oh, all I need to do is plug in. Let's see, CV is 0.73 kilojoule per kilogram degree in Kelvin. And then I have 525 minus 290 degrees Kelvin. The Kelvins cancel out and I get kilojoules per kilogram. And the minimum work then, W1 to 2, actually there's a negative sign. I guess I better keep my negative sign. All that's going to happen is it's going to indicate that it's worked on the system, and I'm immediately going to flip the sign on, okay, to indicate that is the work on the system. Let's see here. So, minus 171 kilojoule per kilogram. Minus 171 kilojoule per kilogram. In other words, in other words, W min equals minus W1 to 2 is equal to 171 kilojoule per kilogram. That's the minimum work required to compress the air. Reversible compression is adiabatic. The minimum work is 171 kilojoules per kilogram to compress the air up to 800 kPa. All right? So that's for constant specific heat. That's for constant specific heat. So in fact, right over here, I'm going to write that result. So for part A, W min is 171 kilojoule per kilogram. So I'm going to write that right over here. We're going to compare our result for variable specific heat next. Okay? So let's do variable specific heat. So I'm going to take this equation and get rid of everything involving constant specific heat. Still the same process, but now we need to find U at state 2 using our reduced pressure stuff, okay? So let's see here, we have U delta, negative delta U, which is negative U2 minus U1, which is U1 minus U2, which is U evaluated at a temperature of 290 degrees Kelvin, and then I just have U2 right here, all right? That's basically what I got. Let's look up U1. Let's look up U1 here. So U1 is U evaluated at 298 degrees Kelvin for air, and I go to my IGB table. Let's see here, air IGB, 290 degrees, 206.091. 206.91, sorry about that. 206.91 kilojoule per kilogram, okay? So I've got U1 right now. That looks good. I've got U1. Now, what about U2? Well, remember when we have variable specific heats, we have PR2 over PR1 equals P2 over P1. So this implies PR2 equals PR1. I don't think, let me go over here. I got plenty of room on the other board. In fact, I need to turn this thing off too. So let's go over here. We want to find it for variable specific heat now. I forgot to put no change in kinetic and potential energy on my assumptions. Please put it on yours. Okay, so variable specific heat. So recall, for isentropic process, we have PR2 over PR1 is equal to P2 over P1, which implies PR2 is equal to PR1, P2 over P1. Now, I've got these pressures, P2 and P1, 800 and 100 kPa. Once I have PR2, I can go into a table and extract out internal energy at state 2. Okay, that's what I'm looking for. In fact, maybe I should be a bit specific here. U2 is equal to U evaluated at PR2. Okay, that's basically what we're doing right now, all right? Okay, so let's see if we can find PR2 and then back out the internal energy from tables at state 2. Let's see here, let's look PR1, that's going to be PR evaluated at, so PR1 is PR evaluated at T1, which is 290 degrees Kelvin. So let's see if we can look that up. Okay, 290 degrees, PR. Let me increase the size here. There we go. maybe a little bigger. There we are. 1.23, 290 degrees, 1.23 is PR. 1.23. Okay, and that's from table, what, B11. That's from B11. See, it says up here in the header, for delta S equals 0. That's what you use, reduced temperature, reduced specific volume and pressure in these columns for isentropic processes. Okay, so let's calculate PR2 and then we'll back out what U2 is. So we got 1.23, it's dimensionless. And then we have the ratio of the temperatures, pressures. So 800 kPa and 100 kPa. And I get 8 times 1.23. And I get 9.84. All right? So PR2 is 9.84. By the way, what temperature does that refer to? T2 is T evaluated at PR2, which is 9.84. Let's see if we can eyeball the temperature in the IGB tables. Let's look for 9.84 in the temperature in the IGB table. Here's 9.68. Here's 10.37. So we're somewhere around 520 degrees. Maybe a little bit, maybe 522. The exact value for temperature is 522.4 degrees once you do a little interpolation between these two data points. So T2 is 522 degrees. And this is interpolated from B11, okay? And of course, U2, which is U evaluated at a reduced pressure of 9.84. There's internal energy, 374. 381, we're a little bit closer to the 374. So it looks to me like around 375, 76 kilojoules per kilogram. So the exact interpolation is 376. 376. 376 kilojoules per kilogram. That is U2. That is U2. So I'm going to write it. I'm going to write it right here, 376. Okay, we have U2 for this isentropic process. So I now have U2, 376 kilojoule per kilogram. Check, that's done. So now we have 206.91 minus 376 kilojoule per kilogram. Let's see what we get. So I get negative 169.1 kilojoule per kilogram. Kilojoule per kilogram. So the minimum work required, variable specific heat, the actual value for work min is going to be 169 kilojoules per kilogram. So this implies work min is equal to minus work 1 to 2 is 169.1 kilojoule per kilogram. So part B, work min is 169.1 kilojoule per kilogram. The more accurate one, provided you did your interpolations correctly, is part B, variable specific heat. Part A, very close, very good for back of the envelope calculations, estimations. So this represents the minimum work required to compress an insulated cylinder filled with H2O, filled with air, from some initial temperature and pressure to the final pressure. The final temperature is about 520 degrees Kelvin, okay?